All right, welcome back to 13.2. We're going to be talking about arithmetic series, and a series is just a sum of a sequence. So we're going to be taking a look at this. Let's jump down to the sum of an arithmetic series, because this is the important stuff. This is what we want to know. So in the book, here's a nice little story about Carl Friedrich Gauss, a mathematician who, as a boy, was asked to add the numbers 1 to 100, right? So if I asked you to add the numbers from 1 to 100, what would you do? Well, you might just start adding them all up, find some other way to do it, who knows? But this kid, as it were, was like, well, that was pretty much 5,050, right? And he just kind of came up with it. So, pretty cool kid. What he did there, which is what we'll see in the book, is he sees the string of 1 to 100, and he kind of thinks of these pairs, right? The 1 and 100, the 2 and 99, the 3 and 98, the 4 and 97. He's like, oh wait, all of those pairs add up to the same number. All those pairs add up to 101. And how many total pairs are there? It's 50. And so 50 times 101 is 5,050. And so he just did it like that, right? And so that's essentially where we're going to kind of take that example and make it a general formula for any arithmetic sequence. So I just want to point out that this formula in the book right here, that's for a specific sequence. Okay, that's only for the sequence of consecutive integers starting at 1, right? We're going to jump to the formula for any arithmetic sequence, right? Even if it's a different constant or a change, whatever it may be. So for this formula, it gives it in two different ways. One of them looks a lot more confusing than the other, so why use that one? Let's go with the easy one. So we're talking about arithmetic sequences here. Let's try that again. Arithmetic series, which, remember, a series is the sum of a sequence. So the formula here, S sub n, so we use S kind of as the sum, is equal to 1/2 times n times a sub 1 plus a sub n. That's the formula we're going to use. Okay, so this is essentially, the sum is 1/2 times n. So this is sort of like, this is the sum of the first n terms, right? So if we're looking for the first 50 terms of a sequence, n would be 50. Okay, so this is the term number in question, I guess. Again, here's our first term, and this is essentially the last term being added, right? So if we're looking for the first 50 terms, we need to know what the 50th individual term is as well. So that's where we would have to use the formula from last class and apply it. So the book uses an example. Let's just make up our own example. Here's a sequence, okay? So I'll just give you a sequence of numbers. So here we go. 1, no, let's not start with 1, that's not fun. How about 7? And then 10, 13, 16. And that's it. Okay? And that goes on forever. let's say, the sequence goes on forever. I want to find the sum of the first, let's say, 18 terms. Okay, well, we should first find a general formula for this sequence. So a sub n equals, what's the first term? 7 plus n minus 1 times, what's the rate of change? 3. Okay? That's the formula from last section. Okay, so to find the sum of the first 18 terms, we're going to be using s sub n equals 1/2 times n times a sub 1 plus a sub n. Okay. So, to use this formula, we need to know the first term and the number of terms we're looking for and the last term. So we need to know what a sub 18 is. So we just plug that in. 7 plus 17 times 3, right? Plugged in 18, 18 minus 1, 17. Okay? So a sub 18 is, let's figure out what that is. What would this be? 30, 51 plus 7, looks like it's 58. So a sub 18 is 58, right? If I continue this going and write down 18 numbers, I want to get to 58. Okay, so now I can do the sum. So the sum of the first 18 terms is going to be 1/2 times 18 times, what's the first term? 7 plus, what's the last term? 58. And so the sum of the first 18 terms of the sequence is, well, let's see, 7 plus 58 times 18 times 1/2 is 585. So the sum of the first 18 terms is 585. And so essentially that's how we use the arithmetic series. So that is kind of like the general way we've done it before. If you haven't used summation notation, I'm going to go over that now. So with summation notation, oops. We use the capital Greek letter sigma, okay, to represent summation notation. So that's this symbol right there. And let's just kind of jot this down in our notes because this is kind of a nice example. So what we do here is this is telling us where we're sort of starting, right? You would sub this number in to this rule. This is kind of like the rule here, or the sequence. And then this is where we're stopping the summation. So in the example I just used for the first 18, what was it over here, right? The first 18 terms, we have a sequence. So I could have written it as this, right? From 1 to 18 of the sequence of 7 plus n minus 1 times 3, right? That was the sequence. And if I calculate that all out, I get that 585. That gives me the whole sum. So that's another way of showing what we did up here. Okay, so it's important to remember that this notation means using the summation. Okay, so whether it be a linear function here or a geometric function or whatever, because we'll get to that later, but whatever the type of function is here or sequence is there, we use the appropriate summation formula. So it's the same thing, it's just like, it's just another way of writing it. It's another way of asking the question, I guess. Instead of writing out, you know, what are the first 18 terms of this sequence, I can just write find this, right? And I can just use that notation. So that's just another way to do it. So let's take a look at the book. So the total number of landscape timbers in n stacks using sigma notation, and give a formula for S sub n. There's no context. Using the context we didn't really go over. So let's go to example 5. Use sigma notation to write the sum of the first 20 positive odd numbers. Evaluate this sum. Okay, this is a good example here. So we're going to do example 5. And the sum of the first 20 positive odd numbers. So we know that that's going to look like 1, 3, 5, 7, and so on. Okay? We know that the first term is 1. We know that the rate of change here is 2. And we know that a general formula for this sequence, a sub n, would be 1 plus n minus 1 times 2. Okay. So the book kind of simplifies that. You don't necessarily have to simplify that, right? The book distributes the 2, combines like terms, and writes it as like a standard mx plus b type rule. You don't have to do that, though. You can leave it in this form if you want. The idea is you just want to make sure you're using the correct notation. So we really like to use the I as the variable. So we would be looking at I equals 1. So from the first term to the 20th, right, the first 20, yep, of this function. I could just write it like this. Okay. Now we do see in the book that they went ahead and distributed and did all this stuff and whatnot. Okay. That's fine too. You can write it in simpler form as well. Okay. Now to evaluate this though, we have to use the sum formula. So we still have to do that same stuff we did before. So we still need to know what is a sub 20. So what's a sub 20? Plugging it in, we'd have 20 minus 1 is 19. 19 times 2 is 38, plus 1 is 39, right? So, okay. And now we're going to plug into our formula. And so we would have 1/2 times 20 times 1 plus 39. Okay? And so what would we get there? 1/2 times 20 is 10 times 40. It's like 400. That's what we do. Okay? The book there uses the different formula for some reason. I kind of like the formula that we use here. It just kind of seems a lot simpler than what the book has done with this business there. So, yeah. I like my way better. Technically, I guess my way is a little longer because I have to find the last term, and they're using this. So if you like to use that that way, please go ahead and do that. That's fine. Whatever works. Whatever works. So there's our arithmetic series, the sum of an arithmetic sequence. That's all we're going to do in 13.2. Next time we're going to be looking at geometric sums and yeah, moving on from there. All right, so hope you're doing well, and I will see you later.